Hey everybody, in this video we're going to be talking about the Chapter 14 review, which covers trig functions and their graphs. For your warm-up, I'd like you to take a look at these four graphs, which are all transformations of the sine function. And I would like you to pick out which graph do you believe doesn't belong with the rest. Okay, there's no wrong answers here as long as you can justify your choice. If you want an extra challenge, you should see if you can make an argument for all four graphs. Why doesn't each graph belong with the other three? Pause this video, make a decision, come up with an argument, and then check back in. All right, so we're analyzing all of these graphs as if they were transformations of the sine function. Y is equal to the sine of x. Okay, and a couple of quick things about this sine function before we look at our choices. Remember that the sine function starts at 0 at the origin, goes up, comes back down, and then finishes the cycle with a period of 2 pi radians. With that in mind, looking at this first graph, I would pick this one out of all of them. It feels like it doesn't belong with the rest because our sine wave starts at 0 and typically goes up, whereas this sine wave starts at 0 and then goes down. So you could argue that this is a vertical reflection of the sine wave, okay? And it would be the only one that starts with that negative slope out of the four graphs. Graph number 2, taking a look at this one on the right. In the past, I've heard folks make an argument that it was actually the cosine function. Since the cosine function starts at 1, goes down, comes back up, and has that period of 2 pi, you could also make an argument that there is a phase shift. And remember, a phase shift is a horizontal shift. So if I'm thinking about the sine function, that phase shift would be to the right until I get to the beginning of the sine function. So it looks like there is a phase shift of 3 pi over 2 to the right. Okay, and both of these first two graphs, the period length has been 2 pi. Looking at graph number 3, this one might have stood out to you because there's clearly a vertical shift. There's no x-intercept here. It doesn't ever cross the x-axis. So the entire graph has been moved up. So you could describe that difference as having no x-intercepts, or maybe there's a vertical shift up, or you could say the baseline has moved. It looks like that baseline is now at 2, so it's been moved up 2 units. For the last one, all right, graph number 4. Okay, there's clearly been some sort of stretch or shrink. You could argue that there's been a vertical stretch, or you could describe it as the amplitude has changed. Normally our amplitude is 1, but now we can see that that's much bigger. It looks like that amplitude is now 3, so there's been a vertical stretch of 3. There are other arguments that I'm sure you could make. Again, there are no right or wrong answers to this question. All right, so here is our concept checklist for chapter 14. Now, the big skill here is graphing, and we need to be able to graph all 6 trig functions as well as transformations of those trig functions. So when I say all 6, I'm talking about the 3 original trig functions that we started with, sine, cosine, and tangent, as well as their reciprocals, cosecant, secant, and cotangent. Hey, when we graph these functions, we want to make sure that we have specific points, and those points are labeled on our axes, our x-axis and our y-axis. Right, for those that involve asymptotes, so that would be tangent and the reciprocals, that we have all of the asymptotes that we need, and that those asymptotes are also labeled. We only need to show one period of each graph. As far as the transformation goes, you could see one or more transformations, looking at both horizontal and vertical transformations, stretches, shrinks, reflections, and shifts. Okay, and one of the big things about these transformations is we have to make sure that our horizontal transformations are in factored form. If not, we need to factor them first. Going in the other direction, we're going to need to be able to write equations for trig functions that may have a combination of transformations. And so we could write an equation based off a description. So for example, we could be given some information about a tangent function. Let's say it has an amplitude of 3 and maybe a period of pi over 2, and then we need to write an equation for that. Or we could write an equation based off of some data. So this is like the daylight hours lab. We could be given that data in a table, or maybe it's a graph, or maybe it's a scenario, a word problem, and we need to write a sinusoidal function for that. So either sine or cosine, but making sure that we consider all transformations again, okay, leaving our final answer as a sinusoidal function. All right, so here are two practice problems involving graphing. We have a sine function and a tangent function. I'd like you to pause the video, give these two a try, see what you come up with, see what questions you have, and then check back in with the video. If you're having trouble getting started, I would encourage you to make a list of the values that you see in these functions and then write a quick description of what those values are going to do to the graph, what type of transformations they are. All right, looking at this first graph, I noticed that the parent function is the sine function, but that we've had 3 different transformations occurring to this sine function. When I look at those horizontal transformations, I also notice that it's not factored. So the first thing that I want to do is factor that. If I take out the 2, which is going to be a horizontal shrink, I'm going to have x minus pi over 6 as the other factor on the inside, which means that that shift isn't actually pi over 3 units. It's going to be pi over 6 units for the horizontal shift. Okay, so I like to make a list of these values so that I make sure I don't miss any, starting with the 55. We called that our A value, which is going to be the vertical stretch. Our amplitude was 1, and now it's going to be 55. Okay, and as I write out these transformations, I'm going to build this graph. Okay, I'm going to make the scale on the y-axis be 55 units. My maximum and my minimum are going to be 55 and negative 55 on that y-axis. Next, I'm going to look at this b value, which is going to affect the period. Now for sine, cosine, and the reciprocals, the period starts out as 2 pi, but it's going to depend on what this stretch or shrink is horizontally. So I need to take 2 pi divided by b. So I'm going to take 2 pi divided by 2, which gives me a period of pi. So rather than squish my graph, I'm just going to change the scale of the x-axis to go from 0 to pi, or at least to start with. So pi is going to be the end of that period, so halfway would be pi over 2. Half of that, a fourth of the period, is going to be pi over 4. So my x-axis scale right now is in units of pi over 4. So I have 1 pi over 4, 2 pi over 4. This would be 3 pi over 4. And then we're ending at pi, which is 4 pi over 4. All right, so now on to the shift. Again, that shift I can see after I factor it. So we're looking at a shift of pi over 6. So that's going to be to the right pi over 6. Okay, before I sketch that shift, I'm first going to create a sketch of the sine function with just the stretches and the shrinks. So that would start at 0, go up to the maximum, down to 0 again, then to the minimum, and then back up to 0. Okay, and I'm using a dotted line because I know this isn't my final graph. This is before that shift. Okay, just getting that basic shape with the stretches and shrinks. Okay, now all 5 of these points need to move to the right by pi over 6. So I'm going to move them and label the final location. So moving to the right, pi over 6 would give me a first point at pi over 6. I'm going to need to do some common denominator work. So pi over 4 and pi over 6. Right? I need to add pi over 6 to that. Those are going to have a common denominator of 12. So this would be 3 pi over 12 plus 2 pi over 12. So my new location is going to be at 5 pi over 12. Pi over 2, I also need to increase by pi over 6, so I'm going to make a common denominator of pi over 6. So this would be 3 pi over 6 plus pi over 6. That's going to give me 4 pi over 6, also known as 2 pi over 3. Next up, 3 pi over 4. I'm going to rephrase that as 9 pi over 12 so that I can add a pi over 6, 2 pi over 12. Okay, that's going to give me 11 pi over 12. And then the last one, pi, thinking of that as 6 pi over 6, plus another pi over 6, I'm going to get 7 pi over 6. Okay, so those are the new x coordinates of my points. I'm going to shift all of the points from the blue graph over to those new locations. I'm going to erase some of these arrows. Okay, and then when I connect them, I'm going to use a solid line to show that this is my final graph. Doing my best to make it a curved function, and I'm going to put arrows at the end to show that that graph exists beyond this one period. All right, so now we're going to look at the second graph, which is with the tangent function. Okay, a couple of big differences between the tangent function and the sine function. The first would be the period length. So tangent has a period length of 1 pi rather than 2 pi. And it's also centered around the origin. So rather than go from 0 to pi, we're going to go from negative pi over 2 to positive pi over 2, at least for the parent function. Okay, but I don't have the parent function. I see some transformations here as well. Okay, we're actually going to have 3 transformations. If I take a look at this a value of negative 2, there's a reflection in there and there's a stretch. So that negative 1 is going to be a vertical reflection, and the 2 is going to be a vertical stretch of 2. Okay, just like with the sine function, I'm going to change up the scale to make this graphing situation more efficient. Okay, so the tangent values that we're going to look at are going to have the y coordinate be 1 and negative 1, at least originally, but now we're going to stretch that to be 2 and negative 2. Taking a look at this b value of pi, that's going to affect the period. The period length started out as pi, but now I need to divide by b. Pi over pi means that period length is going to be 1. So between the asymptotes needs to be a length of 1 unit. Okay, so that means my asymptotes on either side of this tangent function are going to be located at positive 1/2 and negative 1/2, because again 0 is the middle. All right, so my first point is going to be at the origin, okay, and then I'm going to have 2 other points on either side, halfway between the middle of the graph, the origin, and my asymptote. So if my asymptote is at positive 1/2 on the right, that means this point is going to be at 1/4. And on the left is going to be negative 1/4. For the original tangent function, before any reflection happens, the graph has an overall positive slope. So it would go up to the right, down to the left. So I'm going to use a dotted line to show what it would look like without the reflection. So in orange, this would be the transformations of the vertical stretch and the horizontal shrink. But that vertical reflection means those points are going to flip upside down. The origin will stay, but then each of these points on either side of the middle of this tangent function need to flip over the x-axis. So now the overall slope is negative. And I'm going to connect these with a curved function, putting arrows at the end of my graph, doing my best to connect them without straight lines. And that would be the final graph. All right, so for the final example here, we're going to look at a word scenario of a cyclical situation, and our task is to write an equation to model this scenario. In each of these, you can assume that these values are going to be oscillating back and forth in a sinusoidal pattern, and you can choose whether you want to write a sine function or a cosine function. All right, so in this scenario, a team of biologists have discovered a new creature in the rainforest, okay? And we're given two pieces of data. It first says that 15 minutes after they start their examination, they note a maximum temperature of 125 degrees for this creature. And then it says a minimum temperature of 99 degrees occurs 28 minutes later. And again, we're going to assume that this creature goes back and forth between those temperatures, going up and down and up and down. The team would like to find a function to model the creature's temperature over time. Hey, I always find it hard to go right from the word scenario to the equation. I'd much rather see a visual representation of a graph to help me transfer this information to a sinusoidal function. So that's what I'm going to do first, is I'm going to create a quick sketch. Okay, and I'm going to have time be my x-axis and temperature be the y-axis. Okay, so 15 minutes in, we have a data point at 125 degrees, and that's the maximum. Okay, 28 minutes later, so we're not told the time, we're just told that it's 28 minutes later. Okay, we have a minimum temperature. 15 plus 28 means that this is 43 minutes into the study, and that second temperature is a minimum of 99 degrees. So we have half of the period between the maximum and the minimum. We would assume that 28 minutes after that, we'd be back up to the maximum, and then 28 minutes later down to the minimum, and over again. Okay, I like to create a cosine model. Okay, and I might have up to 4 or maybe even 5 transformations that I need to consider to create this cosine model. Okay. I personally always like to start with the vertical transformations and the vertical characteristics of the graph, starting with the shift and the stretch or the shrink vertically. Okay. I like to calculate this shift first, looking at where the baseline of that new curve is. Normally it starts out at 0, but I can see now it's shifted way up. This would be the creature's average temperature. Okay, and that's going to give me the vertical shift again, D. So to find that baseline, I'm going to take the middle of those two. So I'm going to take the average of the minimum and the maximum temperatures. So that would be 99 plus 125 over 2, which is going to give me 112. Next, I'm going to calculate the amplitude, which is the distance between that baseline and the extrema. Okay, normally it's 1, but here I'm going to calculate it by taking the maximum minus that baseline so I can see that difference. So I'm going to take 125 minus 112 and I get 13. So my stretch must be 13. Next, I'm going to look at the period and see how that has changed from my original cosine function so that I can calculate this b value. Okay, so our b value is going to be 2 pi divided by the period length. Okay, now 28 minutes isn't the period, that's half of the period. Right, from the maximum to the minimum, that's half of the cycle. So the period would be twice that value. So I need 2 pi over 2 times 28. Okay, I left it as 2 times 28 because those 2's are going to simplify out. So I'm left with pi over 28. Last but not least, we have the shift. Okay, and with cosine, again, it starts at the maximum. So I'm going to think about the shift into the time. How long did it take into the experiment for that creature to reach the maximum? And I can see that it took 15 minutes to get to that maximum. So this is a shift to the right by 15. So I need to have x minus 15 in my function model. The final step is to just write the equation with all of those values plugged in, which would look like this. Just make sure that you leave those horizontal changes in factored form.